Hi viewers, welcome to my tutorial class on mechanics of materials. In today's class also, I will discuss a problem on stepped bar. Let us start. For the stepped bar shown in figure, find the value of load P which completely fills the gap between free end and fixed end, and also there is no reaction force exerted by the fixed end on the free end. So a step bar ABCD is fixed at one end, that is at A, and it is free at the end D. There is a gap here which is 2 mm. Forces are acting at B and C. So this section is uniform in cross section with the area A by 2 and Young's modulus E. But here there is a force acting at C. Since this force is acting, this particular section has to be considered into two sections, since the internal forces will differ in the portion BC and CD. Now, section AB, the area is A and Young's modulus is E. All the dimensions given are in mm, and A is 200 mm square and Young's modulus is 200 gigapascal. So when A is 200 mm square, this particular section AB is having an area of cross section 200 mm square and Young's modulus 200 gigapascal. Whereas from B to D, the area is A by 2. A by 2 means 100 mm square and Young's modulus same as this section 200 gigapascal. So for BC and CD, the area is 100 mm square, A by 2. Since the forces are acting in the rightward direction, which will try to elongate this composite bar, and this elongation will slowly fills this gap. So as the forces increase, the gap gradually closes. The forces applied at B and C are of equal magnitude. So when this force P gradually increases, the gap fills. So we need to find out what amount of force this completely fills without any reaction produced from the fixed end. So there should not be any reaction force acting at D exerted by the fixed end. So if the force increases beyond what is required to fill the gap, there will be a reaction from here. So if suppose the force just required to fill the gap is 30 kilonewton. When P is 30 kilonewton, this gap will be completely filled because that force is just sufficient to fill the gap. Now if you apply 40 kilonewton, still the gap will be filled, but the force is more. After filling the gap, if the force is more than what is required to fill the gap, that will exert a force on the rigid wall. It is trying to elongate. These forces are trying to elongate, but this rigid wall will not permit that, and that will produce a reaction from here. So that should not happen, and this gap only just get filled. So we need to find out the sufficient amount of force P so that the gap will only just get filled and there will not be any reaction from the fixed end E. So that is the minimum value of P required to fill the gap. So alternately we can ask, instead of giving all this no reaction force exerted by the fixed end, you may be asked the minimum amount of force required to just fill the gap. So we know the elongation of this composite bar. So it should elongate by 2 mm. Okay. So what is the amount of P required to just produce an elongation of 2 mm? That is what we need to calculate. Okay. Now let us find out the forces in the various sections. Now let us take a section here and calculate the internal force. Now here you have a rightward force P, and at C also we have rightward force P. So P plus P 2P. So that will be the internal force here. And in the portion BC, if you take a section, considering the right portion, we will get only one force P. So that is the internal force. So we have one force P. This force should not be considered, which is on left side should not be considered. You take the right side portion and consider all forces, taking rightward as positive. Okay. So this is rightward, so plus P. Now when you take the portion CD, here I am taking a section between C and D. Now this force P is applied at C, so we should not consider this. So wherever you take between C and D, there is no force coming on the right side part. This force is acting at C. If you take a section beyond C, this force will not come there on the right side. So the right portion when you take, there is no force acting. So the force acting in this section CD is 0. It is not subjected to any axial force. Only this force is trying to elongate the portion BC and AB. Okay, and this force applied at B is only elongating AB. It is not producing any effect on BC. But this force applied at C is elongating BC as well as AB. Here there is no internal force. So we got the forces in the three sections. Now this force P1, P2, P3 I have written once again here. A1 is 200 mm square, since the portion AB area is equal to A and we are given that A is 200 mm square. So I have written A1 as 200 mm square. A2 and A3 is A by 2. So A is 200, so A by 2 is 100 mm square. So BC and CD sections, you have 100 mm square area, and the lengths of each portion AB, BC and CD, each one is 500 mm. Young's modulus is 200 gigapascal for all the sections. So 200 into 10 raised to 3 Newton per mm square, since each gigapascal is 10 raised to 3 Newton per mm square. Now let us find out the elongation in each portion. Delta L1 is P1 L1 divided by A1 E1, and P1 is 2P. So we know only it is 2P. Twice the value of P is acting in the first section. So we have just put 2P. Length is 500. A1 is 200. And Young's modulus is 200 into 10 raised to 3. So you can write as 2.5 into 10 raised to minus 5 P. In terms of P only you will get. Similarly, delta L2 is P2 L2 divided by A2 E2, and it's equal to P into 500. So P2 is P. And the force in the second section is only P, and length is 500. A2 is A by 2, which is 100. We have calculated here, into 200 into 10 raised to 3 Young's modulus. So it is also coming to 2.5 into 10 raised to minus 5 P. Same, here force is double, but here the area is half, area is reduced. So that has compensated and is giving the same deformation in the first section and second section. So that means in the first section the force is 2P. Both the forces are acting for the first section. The force is more, area is A. In the second section BC, force is only P. It is reduced to half, but area also correspondingly reduced to half. So the elongation produced in both the sections are equal. Now delta L3, since P3 is 0, there is no force acting in the portion CD. P3 is 0. Okay. So the elongation in that portion is 0. So total elongation is going to be summation of all these, and delta L3 is 0. So it is delta L is delta L1 plus delta L2. So you can write down that, and we also know that total elongation should be equal to 2 mm. So 2 mm is equal to 2.5 into 10 raised to minus 5 p plus 2.5 into 10 raised to minus 5 p plus 0. We have seen that all these units are consistent while substituting. So this is in mm, this in mm square, and we have put Young's modulus is Newton per mm square. So now it has to be in Newton, because this we have used Newton per mm square. Force unit is Newton. So P will be getting in Newton. Delta L2, this is all in mm. Okay. So we need to substitute delta L also in mm only, 2 mm. So substituted this and we can solve for P. So this 2.5 into 10 raised to minus 5 p plus 2.5 into 10 raised to minus 5 p. Since 10 raised to minus 5 p is common in both, 2.5 plus 2.5 we can add 5 into 10 raised to minus 5 p. So p is equal to 2 divided by 5 into 10 raised to minus 5, which will work out to 40,000 Newton. So 40,000 Newton is 40 kilonewton. So this is the amount of force that has to be applied at point B and C to just elongate the bar and fill the gap without reaction from the fixed end. That's all for today. Thank you for watching.